In this video, I want to introduce differentiation. So differentiation is the branch of calculus that deals with instantaneous rates of change. Now, back in year 9 or year 10, when we started looking at rates of change, we looked at something called a travel graph or a distance time graph. So this is an example of one of those graphs. And what you can see is that the object's moving forward or away from its starting point, then it stops, it starts moving away again, stops for a second time, and then it returns back to its starting point. One of the things we focused on when we introduced these was calculating speed, and you can tell the speed of the object that's moving by the gradient of the line. So if we compare these two sections here, you can see that it's moving faster in this first section because the line is steeper, compared to up here where the line is less steep, so it's going slower. And in these two sections where the object has stopped, the line is horizontal. The problem with distance time graphs or travel graphs though is that in reality objects don't move like this. They don't instantly go one speed, a constant speed, and then instantly stop, instantly start moving and maintain that exact same speed until they stop again, and then instantly start moving again. Things change gradually over time. So what this graph should more realistically look like is this one. So instead of having sharp corners on our graph this time, we have gradual changes. The good thing about these though is it's easy to interpret. With these ones, if I wanted to know the speed of the object at an exact point, so say I wanted to know the speed of the object at that exact point, we don't know the gradient at that point. If I wanted to know how fast the object was going here, I could figure that out just by finding the gradient. But this one, I don't know the exact gradient of that curve at this time. So this is what we're going to have a look at in this video, is how to find the gradient of a curve at an exact given point. So to work through this, we're going to have a look at a slightly easier example, a slightly more basic curve. And say I wanted to find the exact speed of the object at this point in time here. So I'm going to call my curve, I'm going to call it f of x. And I'm going to say that we know the equation of the function that gives this curve. Then I'm going to call this value, I'm just going to pick an x value here, and I want to know the speed of that object at x. Now, if I wanted to do that, one way that we can do that is to consider the gradient of a secant. So a secant is if I picked one point down here, for example, and one point up here, then I could draw a straight line between those 2 points. So we've picked 2 points on our parabola, one on either side of the actual point we want, and we've drawn a straight line between them. Now we could find the gradient of that line and it would approximate the gradient at that point. So if we called this x1 and this point here, we'd call that x2. Then the coordinates of these points, this point here would have coordinates x1, and then to find its y coordinate, we'd substitute that x value into the function. So its y coordinate would be f of x1. Now this point here would have coordinates x2, f of x2. Now that we've got the coordinates, we know our gradient formula and we could find the gradient of that straight line. We'd have to find the gradient, we would subtract the y coordinates, so we'd have f of x2 minus f of x1 over the difference in our x coordinates, which would be x2 minus x1. But you can imagine that that's not going to be perfect. It's not going to be very close or very accurate. So what we can do instead is we can bring those 2 points closer together. So say I put my points here and here instead. If I draw my straight line between those 2 points as best I can on here, then you can see that that's a much better approximation of the gradient at that red point. So I could do the same thing. I could find the gradient of that line, and that would tell me approximate the gradient at that red point that we actually want. Now, the closer and closer those 2 points get, the more accurate it's going to become. So just to demonstrate that to you a bit more neatly than what I can draw, we've got in GeoGebra here, we've got a curve that's similar to our one. We've got a point, and this point here is what I want to approximate the gradient at. And then I've picked 2 points, one on either side of our original point, and we've drawn a straight line through them. So if I move those 2 points closer to my point that I actually want, you can see that it's getting to be a better approximation of the curve at that point. But if we zoom in, you can see that it's still not perfect. So if I move them closer together again, it's looking like a pretty good approximation. Now, if I were to find the gradient of that line between those 2 points, that would give me a pretty good approximation of the gradient actually at that point. Now, if I move them really, really close in together, and then I zoom out, we can see what we actually end up with. So if I zoom back out, you can see that as those points have gotten closer and closer and closer to the actual point that we want, the line that we've drawn is actually just the tangent to the curve at that point. So ideally, what we want is the gradient of the tangent to the curve at our given point. So if we jump back to our diagram, I want to have a look at how we can generalize that. So what we're going to do is to find the gradient of the curve at an exact given point, we're going to try and find the gradient of the tangent to the curve at that point. So what we're going to do, we've picked our point x here, and we know that that point has coordinates x, f of x. Should have drawn that somewhere else. Now I want to pick a point that's really close to it. I'm going to draw it up here, just because I can't draw it infinitesimally close, because then we can't read it. And I'm going to say that this point has the x coordinate x plus h, where h is just a number. So I've gone from wherever we are here at x, and then I've added a little bit, which I've called h. So this point here would have coordinates x plus h, f of x plus h. Now, if I wanted to find the gradient of the straight line between those 2 points, I'd use my gradient formula. So I'd have f of x plus h minus f of x over, and then I would subtract my 2 x coordinates. So I'd have x plus h minus x. Now that x plus h minus x, they will just cancel out, and I'll just have a h on the bottom because my x's cancel out. Now when we've got this, that h, we want it to be infinitesimally small. We want it to be that close to 0 that it's not even funny. So we want to get it smaller and smaller and smaller and smaller. So what we're going to do is we're going to use something called the limit. And we haven't actually looked at these yet, but we'll come and look at them formally and in a bit more detail later on. But what we want to do is take the limit of this function as h approaches 0. So we're going to say as h is getting tinier and tinier and tinier, what does this approach? So this is what we call the first derivative. So we use the notation f dash x or f prime x to denote the derivative of a function f of x. So we'll write it like this, and this is actually on your formula sheet. So in the next video, we'll have a look at some examples of how you actually use that to find the gradient, but that's an introduction to differentiation.